Right, so here we go with A2 Physics from CCEA, and this is Fields in Their Applications from June 2016. Let's get started. Question 9 is a synoptic kind of question. It says that some features of petrol engine lawnmower are identified in figure 9.1. We've got the speed control, the tension pull string, the petrol combustion engine. So they then talk about the pull string and a vibration on it. It says the vibration of the engine causes the tensioned pull string to vibrate. A standing wave is set up on the tension pull string, see figure 9.1, when the speed control is in a specific position. So obviously you can vary the speed of the engine, and at some particular engine speed, this wave that we can see here is set up on the pull string. So we're told the details of the pull string. We're told that it's 76 centimeters long, and we can see how many waves in terms of nodes and antinodes that we get here. Part 1, show that the engine is rotating at 3.6 times 10 to the 3 revolutions per minute when the standing wave shown in figure 9.2 is produced, and the speed of the wave on the tension pull spring is 18.3 meters per second. Assume that the engine RPM numerically equals the frequency of the vibration of the progressive waves that are set up in the standing wave on the tension pull string. Now this phrase they've used here is a bit confusing, and I think what they're trying to say is that if you can find the frequency of the engine making rotations, that will be the same as the frequency of the vibration. And they get a bit confused when they use the term RPM and frequency, which we would expect to be in hertz. But we will assume that the frequency of the engine making revolutions is the same as the frequency of the vibration. So part of our job here is to get a frequency from this diagram, and you can see here that the wavelength would be that far. So each one of these bumps is like a half lambda. So we've got 1, 2, 3, 4, 5. So it's 5 lambda over 2 equals 76 centimeters. That's really what we've got there. So 2.5 lambda equals 0.76 of a meter, which means that lambda will be that value over 2.5, which is 0.304 of a meter. Now we already know that V is 18.3 meters per second, and we also know that F will be equal to V over lambda. And that gives us a frequency of about 60 hertz. So hertz, remember, is vibrations per second. RPMs, revolutions per minute. So to convert from vibrations per second to per minute, we would need to multiply by 60. So that's what we do, and we get a value then of 3600 RPM. And that's what they told us it would be. So we were asked to show that that was true, and we have. So part 2 then. In the engine, the piston moves in simple harmonic motion within its cylinder. Estimate the maximum force acting on the piston of mass 120 grams that moves a maximum distance 86 millimeters from its equilibrium position when the engine rotates at 3600 RPM. So this is standard simple harmonic motion stuff. We've got the idea that we can get the acceleration from the simple harmonic motion equations, and then we can apply Newton's law that F equals ma to give us a force. So we've got F equals ma, and A is omega squared x, well, minus omega squared x. But A max is going to be when the displacement is the maximum at the amplitude. Okay? And omega is going to be theta over t, the angle turned over how long it took. And we've got 3600 complete revolutions, which is 3600 times 2 pi, divided by how long that would take, which would be a minute, with 60 seconds. So that's our value for omega. And the maximum x, that is the amplitude of this vibration, is going to be 86 times 10 to the minus 3 meters, 86 millimeters from the value they've given us. So F equals ma, which equals m omega squared x. So we've got 0.12 of a kilogram times the omega squared value, and squaring that, and then multiplying by the x max of 86 times 10 to the minus 3. And I'm getting 1466.7. Okay, so 1467 would do. Part B, the spark produced by a spark plug is used to cause the fuel air mixture in the lawnmower engine to combust. This produces the force that moves the piston. A typical spark plug shown in figure 9.4 produces a current of 13.6 milliamps through a 0.8 millimeter spark gap and converts 0.03 joules of energy in a time of 1.20 milliseconds. Calculate the potential difference across the spark gap. So if you remember from your electricity notes that W equals QV, the work when a charge Q crosses a voltage, and that Q equals IT, the charge passed when a current passes for a time, you can combine these into an energy equal to ITV. So IT being substituted for Q gives you W equal to ITV. So V is going to be W over IT. Then we just fill that in. So we've got 0.003 joules from here, and we've got 13.6 milliamps from here, and we've got 1.2 milliseconds from here. And that gives us a V when we follow that through of 1838. So we're then asked how many electrons will reach the positive terminal of the spark plug in the 120 milliseconds that the spark lasts for. So the total number of coulombs will be just Q equals IT, and the number of electrons will be that charge divided by the charge on one electron. So you're going to have N is going to be Q over the electron charge, which means we've got IT over the electron charge. So we just fill that in now. So we've got an I value of 13.6 milliamps, a T value of 1.2 milliseconds, and a Q, or an electron charge value here, of 1.6 times 10 to the minus 19. And that's giving me 1.02 times 10 to the 14 electrons. Part C. A petrol lawnmower emits a sound that has an intensity level 92 dB at a distance of 0.1 meter from the engine. Calculate the sound intensity level experienced by someone using the lawnmower if their ears are 2 meters from the engine, where the intensity is 1/400th the size it was at 0.1 meter from the engine, and the threshold of hearing is 1 times 10 to the minus 12 watts per meter squared. So your formula sheet has this equation that the sound intensity level is 10 log base 10 of I over I naught, where intensity level is of the I value and I naught is this threshold of hearing. So this value they're telling us here is the I naught value. I is the intensity that we have, which they're telling us is 1/400th of what it was at 0.1 when it was 92 dB intensity level. So if you imagine that an intensity I1 is the value at like 0.1 meter out, it has an equation that says that 92 dB is equal to 10 log I1 over I0. Okay, but the other thing that's true is that this I2 value that they're talking about when we are 2 meters out equals I1 over 400. It's a 400th of the original intensity. So what we can do is say that I2 times 400 is the same as I1, and that means this can be put into the original equation, so we can write that 92 equals 10 log base 10 of I1, which is like 400 I2 over I0. So what we've done is we've just taken the original I1 and put in what it's equal to in terms of the second intensity. So I1 is 400 times the second intensity, but it's okay to put that in there like that. So dividing both sides by 10, we get that 9.2 is the log base 10 of 400 I2 over I0. So if we take antilogs of that, we can say that 10 to the power of 9.2 equals 400 I2 over I0. So I2 then equals 10 to the power of 9.2 times I0 over 400. So I0 times 10 to the 9.2 all over 400. I'm just sub in for now I0 now, this value that we've been given, a 1 times 10 to the minus 12 for the threshold of hearing. So we've got our threshold of hearing value multiplied by 10 to the 9.2, which is the antilog of 9.2, and divided by 400. And I get that to be 3.96 times 10 to the minus 6 watts per meter squared. And you put that back into the intensity level equation of 10 log of that value over the I0 value of 1 times 10 to the minus 12. And that gives you like 66 dB when you do that. 65.97 or something like that. But there's a massive shortcut to this question. You can do an intensity level difference if you don't use the threshold of hearing. If you use this equation with like I2 over I1, you get the intensity level difference. So the intensity level difference is 10 log of I2 over I1, which is then like 10 log. Well, the difference between these two is like 1/400th. Because I1 is 400 times more intense than I2. And if we do that, we get minus 26 dB. In other words, that's what needs to come off the 92. So the second intensity level is 92 minus 26 dB, which is the 66 that we've got. Obviously, there are lots of different ways to do this, some of which are a heck of a lot quicker, and some take a bit more effort. Okay, thanks for watching.